am gonna oh, hello. Okay, we're recording now. Okay, just gonna give it a couple more minutes, couple more seconds. Okay, while we're waiting for the few others that were in Collaborate to pop in, I have your chapter 19 Pearson homework up and available to you. Like I said, it was going to be a little bit more extensive than the other ones, simply because you're not being tested on it before your final. The focus in chapter 19 is going to be redox, balancing, and acidic and basic conditions, and then the voltaic cells and cell potential. Okay. And with that, again, I put a due date on there, but really technically it's not, none of the assignments are due till the day of the exam. But moving forward into the semester, my surgery is Tuesday. So obviously I'm not going to be in class. I'm going to try to get one of the Dr. D's to cover for me. If I can't get one of them to cover my class, I'm going to put a video up with a lecture video up with an assignment. But I'm going to try to get either one or both of them to cover, the two sections. Are you guys done with lab now? Is lab over?
We just have oral presentations left.
Okay, and you're doing that this week or next week?
I think it's this week for Dr. Antonio.
Okay, and I don't know what Dr. Gibson is doing. He does different things. Okay, but you're done with lab, so really all you got are your presentations. Treat them, I'm telling you this, especially if you have Dr. D, treat those oral presentations like a business proposal. Dress the part, have the part, don't be just reading every word on your slide. Have your slide up with bullet points and talk about it. Make sure it's, you have pictures in there and everything is labeled. Like, treat it like a business proposal that you're giving to your bosses. Okay, that's the best way, especially with Dr. D, how to handle those. Okay. All right, I'm going to go ahead and get started. Again, recap, my surgery is Tuesday, assuming I don't get sick again. I'm going to try to get one of the Dr. D's to cover for you guys. If they can't do it, I'm going to put a lecture video up with an assignment. Okay, I just want to share the screen. I don't know what that is. I don't know what that is. I'll mix it out. Seriously. All right. How do I get rid of this? Guys, how do I get rid of this panel? Oh, well, that will get me rid of that. Okay, none of that's helpful. Okay. Man, seeing that's it, I shared the wrong screen. Why is it doing this? Okay, so When, excuse me, hopefully you guys watched the videos and you maybe remembered some of the redox stuff from Gen Chem 1. If you didn't, hopefully you went back and reviewed. But we're going to focus today on assigning the oxidation numbers, just generically speaking, and then balancing in both acidic and basic conditions. So I'm going to start with D. Why isn't this letting me write? I'm going to start with D. And we'll kind of go through the rules as we go through all of these. I'm going to do B. I'm going to do this B. I'm going to do this D. Okay. All right. So when we look at Mn2O7, each one of these is going to be assigned an oxidation number. Now, you got to remember, an oxidation number, it is not a charge. It's the state of oxidation. All right. So there's a few rules we can follow, which make it pretty easy to figure out the positive or the one that gets the positive oxidation number. Generally speaking, when we have more than one thing in solution, like a compound like we see here, generally speaking, we're going to be solving for trying to figure out the oxidation number for the metal or the one that will hold the positive oxidation charge, because there are certain rules. For example, oxygen always gets an oxidation number of 2-, always and forever. Okay, it gets an oxidation number of 2-, unless the only exception is if it's in a peroxide, then it gets a 1-. So a peroxide, for example, would be H2O2. Okay, so anything here, O2 is usually considered a peroxide. So in which case oxygen would be assigned a -1. But things like oxygen, fluorine, etc., I can't think of an example when they don't get the negative oxidation number. And that's because of their electronegativity. All right, so when you're looking at this, the oxidation numbers either have to net out or add up to 0, like because this is neutral, or for example, in something like D or B down here, they would have to add up to whatever that charge is. So if we know that oxygen is 2-, and in this case, there are 7 of them, the whole thing's got to equal 0. No idea what the manganese is, but there are 2 of them. So if I solve for X, I can figure out the oxidation number on that manganese. So we know oxygen is going to be 2- because that's our rule. So just doing the math here, we're going to have 2X minus 14 equals 0. X is going to be plus 7. So the manganese oxidation number is plus 7. Okay. All right. Pretty straightforward. Okay. Let's look at copper 2 sulfate. We got 3 things going on here. Oxygen, we know, is going to be 2- because that's our rule. Now, sulfur and copper, what do we do with these? Well, copper is going to be positive. And in this case, sulfur is going to be positive. Generally speaking, we say sulfur will be, a negative oxidation charge. But if it's there with oxygen, oxygen trumps sulfur getting the negative oxidation number. Okay, so sulfur is generally a 2- charge. And generally, if it's not with an oxygen, we're going to see that it'll take on the oxidation number equal to its charge. Sometimes it just happens, just remember it's not a charge. But in this case, sulfur is positive because oxygen gets first dibs on the negative oxidation number. So sulfur is going to be +2. So now we just have to figure out what copper is. So copper is going to be, I don't know. There's 1 sulfur, so +2. Hello? If you have a question, just unmute yourself and ask. Okay. What did I just do? There we go. All right, so X for the copper, sulfur is going to be +2. Oxygen, there's 4 of them. And each one is 2-. So we're going to have X +2 -8. Whole thing's got to equal 0. So X is going to be +6. Okay, that's just basic math. And doing it this way to solving for the oxidation numbers always works, always and forever. Okay, so now let's look at number 2B. Again, oxygen, it's going to be 2-. Sulfur, we have no idea. But in this case, the whole entire thing must equal -2. So we're going to have X plus 2- times the 3 that are there. Eek. The whole thing's got to equal -2. So X minus 6 equals -2. +6 +6. So X is going to equal +4. So the oxidation number assigned to this sulfur is going to be +4. Okay. All right. Why don't you guys do NO2-? Okay. So you should have gotten this. So that oxygen is 2- and nitrogen is +3. Okay. All right. Now let's put this into practice. We're going to start. I know it says balance, but I'm just going to start with just figuring out the oxidation state of each thing, because we have to do that in order to know what is oxidized and what's reduced. If you remember from the lecture video, and you might have learned this in either Gen Chem 1 or maybe if you took high school chemistry, oil rig, oxidation is loss, reduction is gain. So I'm going to start with the manganese because it's easiest. Over on the reactant side, the manganese has a +2 charge. And when you have a monoatomic ion, the oxidation number is that equal to its charge. So the manganese here is 2+. This manganese over here, we're going to have to solve for. Where are my little tools? I need an eraser. Hang on. Why isn't it erasing? Maybe because I need to do it in PowerPoint. Hold on. Trying to figure out the Zoom whiteboard, y'all. Nope, don't want to do that either. Got it. Okay. All right. So if I go over and I say, okay, MnO4 minus. So the manganese changes from a +2 oxidation state to +7. Okay. If I'm going from +2 to +7, is that a gain or loss of electrons?
Loss.
Loss, you are correct. So that means this is a loss of 5 electrons, and that's going to be my oxidized side. All right. So what I'm going to say is I'm going to say Mn is my oxidized side. 2 plus is going to yield MnO4 minus plus 5 electrons. Okay. Now I'm going to look at the lead. We'll go down here. Okay. Goes from, we got that one is 2 plus. It's a monoatomic ion. So with the monoatomic ion, the oxidation number is equal to that of its charge. So now we just got to figure out the PbO2. So PbO2. So it's going to be X plus -24 equals 0. So it's going to be +4. Okay, so going from +4 to +2 is a gain of electrons. Okay. Okay, so let me go back and get my eraser. All right, so my redox side is going to be PbO2 plus, how many do we say? 4? No, it was 4 and then it went to 2. So 2 electrons yields Pb2 plus. Okay, so that's our redox side and our oxidized side. Now, when we're balancing in acidic conditions, what we're going to be dealing with mainly is water. Let's do green. Okay, so the first thing I have to make sure, and I like to split these up and just balance as is first. Meaning I'm just going to worry about oxidized, then I'm just going to worry about the the reduced half, and then I'm going to put them together. So when I look at the oxidized half of my reaction, manganese is balanced. There's one manganese here, and there's one here. Okay, so I don't need any coefficients. I'm good there because they're balanced. But I have oxygen on the product side. I have oxygen over here, and I have no way of balancing it opposite. So what I'm going to do is I'm going to add water. And I'm going to add the number of waters equal to the number of oxygens that I need to balance. Now remember, I'm not just magically coming up with water from somewhere. The water is in solution. These are aqueous solutions. So it's not like I'm just magically pulling water up out of the thin air, okay? So I'm going to add the number of waters equal to the number of oxygens that I have to balance, okay? Okay, now the problem is I got my oxygens balanced, right? I got 4 oxygens from the water, 4 from the MnO4 minus, but now I got these hydrogens I have to deal with. So what am I going to do? Opposite the water, I'm going to add the number of hydrogen ions that are present. So H2 from H2O, and then there's 4 of them, so that's 8. So I'm going to add 8 hydrogens opposite. Okay. Now that's done. I got nothing left I need to balance. Oops, let's make that actually look like an 8. Okay. So my hydrogens are balanced, my oxygens are balanced, my manganeses are balanced. Good to go. Now let's move on to the redox half. And I'm not going to write underneath here because I'm kind of running out of room. I'm just going to pull it down below, but I'm going to maintain the green for adding the waters and hydrogens. So I'm looking at the PbO2 and the Pb2 plus. Those are balanced. There's one of each. There's 1 Pb of each. Doesn't matter that one has a charge and one doesn't. So those are balanced. But now I got to deal with the water again. Okay. So when I deal with the water, I'm going to add water opposite the oxygen that I need to balance. So it's PbO2 plus 2 electrons yields Pb2 plus I have 2 oxygens. So I need to add 2 waters. Okay. Those 2 waters are going to balance out my oxygens. And now I got to deal with the hydrogens. Now I got to deal with the hydrogens. And I'm going to add 4 hydrogens opposite the water. Okay. Now, when we kind of add this all up together and cancel what we'll cancel, what we're going to see is that, oh, and that's the other thing. I'm sorry, I forgot to do the electrons. Can't forget the electrons. So in order to make the electrons balance, I need a different color. I got 5 being lost and 2 being gained. So what I got to do is I got to do a multiplier here. I'm going to do that one by 2. And this one by 5. So now what I'm going to have is, let's see, 8 waters. Plus Mn2 plus yields MnO4 minus with my coefficients in front, plus 10 electrons plus 16, am I counting correctly? Just plus 16 hydrogen ions. Okay. And then for the second one, it's going to be 20 hydrogen ions plus 5 PbO2s yields 5 Pb's 2 pluses plus, oh, I forgot to write the electrons. Ugh, get ahead of myself. Let me just write this down and then we'll talk about it. Okay, so now that we have that, we're going to cancel out what cancels to make sure everything is balanced appropriately. Okay, so my 10 electrons cancel out. That has to be of number one most importance. Okay. I have 10 waters. That's going to become 2. And all of these are going to cancel out. This will stay. This will stay. This will stay. This stays. This stays. Now, these will be canceled out by those. So I will have 4H pluses that 4H pluses that stay. Okay. All right. So putting all this together, just go back and grab my eraser. Putting all this together, your final balanced in acidic conditions reaction is 4H plus getting frustrated, y'all. I don't like Zoom nearly as much as I do Collaborate. It's much easier to use. Plus 2Mn2 plus 5PbO2 yields 2MnO4 plus 5Pb2 plus 2H2O. Okay, that would be your overall balanced reaction, balanced by using half reactions and in acidic conditions. And what makes this the acidic conditions? What a gift from you, Zoom. What makes it the acidic conditions? This right here. Okay, you have to remember 2 things. First of all, this is being recorded, so when I erase this whole slide, you will be able to go back and fill in any of the blanks. But I'm gonna actually, let me just do this. I'll come up here and erase this stuff first, and then I'll erase the whole slide. Okay, there's a couple of things you have to remember. The first one is, if I just have water in solution, at any given point, both this and this and this, one of those 3 species are in solution at all times. And the other thing you have to remember is that we interchange or interuse these 2 terminologies. They mean the same thing. So when I have hydrogens left over in solution, that's in acidic conditions. Okay. All right, any questions about this one? If you're confused or have questions, now is the time to ask. Just unmute yourself because I'm not paying attention to the chat box. No, all right. Okay. Now, let's look at number 5. Okay. So number 5, I'm going to use the top half of number, like the space for number 4 to help me with number 5 so I don't run out of room. Okay. All right. So let's start with BR2. Just because I feel like it and it's easier. It does not matter what you start with. It does not matter what order you write them in, as long as the correct things are on the both left and right hand side of the arrow. Okay. Also, you'll note I'm kind of focusing on cations, or what's in front anyway. And that's because everything I've had so far has been oxygen as an anion, and that it doesn't change. It doesn't change. So oxygen is 2 minus is 2 minus is 2 minus. So, you know, I can just kind of ignore it. It's going to stay as is. So I'm going to go from 0 because BR2 is in its free state. Why does that matter? Why do we say it's 0 when it's in its free state? Okay. It's in its free state, meaning it's how it naturally occurs in nature. Anything that naturally that is present as it naturally occurs in nature is in what we call its free state. Okay, so that gets an oxidation number of 0. If there is no charge, if it is not involved in a bond, and it's how it naturally occurs in nature, its oxidation number is going to be 0. All right, and then Br minus, that's pretty easy, goes to 1 minus. Okay. And then I'm going to ignore oxygen. We're going to look at sulfur. We just did this one on the previous page. So we know for HSO4 minus, sulfur's +6. All right, let's figure it out for SO2. We know oxygen is 2 minus, and there are 2 of them. Sulfur, we don't know, so that's going to be X. Whole thing's got to equal 0 because the overall compound is neutral. So sulfur must be +4. So we go from 0 to -1. That's a gain of 1 electron. And going from +4 to +6 is a loss of 2 electrons. Okay, so our oxidation half is SO2 yields HSO4 minus plus, how many do we say? 2 electrons. Okay, and then our redox half, or our redox half, wow, our reduced half is Br2 plus 1 electron yields Br minus. All right, I'm going to start with the redox half because it's the easiest one to start with. There's 2 Brs on the left because it's Br2. So I need to throw a 2 in front of that Br. Okay. So that's balanced. And then for the redox one, there's only 1 electron, but the oxidized half is dealing with 2 electrons. So I'm going to be multiplying all this by 2. Okay. All right, so 2. I'm in the middle of teaching a class right now. Can you come back? Sorry. Okay, so then 2 and then 4, because I had to multiply all that by 2. So the number of electrons gained and lost are equal. All right. Now, so that one's done. It's balanced. Everything is good. I don't have to do anything to it. There are no oxygens present. Super easy peasy. Okay. Now let's go deal with the oxidized half. My sulfurs are balanced. Got hydrogens I'm dealing with, but I'm going to hold off with trying to balance those because I have oxygens that I want to deal with first. It's going to be much easier for me to deal with the oxygens first. Now, the difference here is I have oxygens on both sides of my arrow. So we know that we need to add water equal to the number of oxygens I have to, balance. So if I have 10 oxygens I have to balance, I put 10 waters opposite it. If I have 3 oxygens I have to balance, I put 3 waters opposite it, okay? But now I have oxygens on both sides. And if I just put a 2 in front of this sulfur here, then that's gonna mess up my sulfurs being balanced. So I can't do that. I'm gonna have to add the water. The question is, to what side do I add the water? Where do you think?
The left,
The left-hand side. And how many am I going to be adding?
just 2.
Just 2. Yes, exactly correct. So 2 H2O plus SO2 yields HSO4 minus plus 2 electrons. Okay, so now what do? I got 4 hydrogens. I got 1 hydrogen here. I need to add hydrogens opposite the water. So how many am I going to add and where am I going to add them?
Three on the right side.
Got it. Oh, I forgot to change to green. Sorry. I'm trying to maintain colors. Okay, so I got my 1 sulfur, good to go. I got my 4 oxygens, 1, 2, 3, 4 oxygens. I got my 4 hydrogens, 1, 2, 3, 4 hydrogens. So I got 1, 2, 3, 4, 1, 2, 3, 4. Okay, good to go. Now, all of that is balanced. So if I go to put them together, I'm just going to bring this one up here because it's quicker to write. Okay, now what's going to cancel in this case? The only things that are going to cancel are these 2 electrons. Okay, so my overall balanced chemical reaction in acidic conditions here would simply be 2H2O plus SO2 plus 2 Br2 yields 4 Br minus plus H SO4 minus plus 3H plus. Now, again, what makes this acidic conditions is the fact that that right there is present. Okay, that would be your overall reaction that is balanced by way of using half reactions in acidic conditions. Okay, so now let's talk about it in terms of basic solutions. All right, I'm going to look at number 7. All right, so I'm going to look at aluminum first, just because I feel like it and no other reason. It's going to go from 0 because aluminum is in its free state. We know it's in its free state because it's not involved in a bond. It does not have a charge, and it's occurring how it naturally does in nature. So free state, oxidation number of 0. Okay. Now, this one over here, let's figure it out. All right, let's talk about hydrogen. Hydrogen, generally speaking, is going to take on a +1 charge, not charge, I'm sorry, oxidation number, unless, of course, it is, with another metal. If it's the most electronegative thing. If it's not, it's going to go ahead and it's just going to take on that +1 oxidation number. We know that oxygen is -2. So this is going to be +1. This is going to be -2. And we got to figure out aluminum. We have no idea. So we're going to have X plus 4 times 2 minus, which is -8. And 4 times +1, so that's +4. Whole thing overall has got to equal 0 because it has or not a 0, -1 because it's got a -1 charge overall. And so you're going to have X minus 4 equals -1. Did I count right? Yes, I did. And so X must be +3. Okay, 0 to +3, is that a gain or loss of electrons?
Loss.
Got it. Loss of electrons. Okay, so I'm going to put, that's my oxidized half. I'm going to go ahead and put it up here. So it's AL. AL. 1, 2, 3 plus 3 electrons. Okay. All right. And then let's see, what should I look at here? I'm going to focus on the Bi. And the reason I decided to pick that one as opposed to looking at the nitrogens or the hydrogens, because for 2 reasons. One, I can see that it goes from involved in a compound to its free state. So it's doing something. It's going from something to 0. So more than likely, that's going to be my reduced half. But the other reason is, A, oxygen is oxygen is oxygen, period. And then the hydrogen with the nitrogen is more electronegative than hydrogen, so that's going to be +1. And there's no hydrogens on the left-hand side, the reactant side of this equation, in order to say, oh, well, it changes. Okay, so let's just figure out what Bi is. So I got 1, 2, 3, 4. So it's going to be -8. Nitrogen will take on the positive oxidation number equal to its charge. Overall, there's nothing happening, no, it's neutral overall. So X must be equal to +5. So it went from +5 to 0. And so that is a gain of electrons. And it's a gain. And that will be my reduced half. And I'm going to go ahead and erase all of this. Okay. All right. Now, I'm going to start with the oxidation half and balance that for no other reason, but I feel like it. You can start with either the oxidation half or reduction half. It does not matter. I'm just going to start with the oxidation half. Okay. Now, the aluminums are balanced, so I don't have to do anything there. I got 4 oxygens on the right-hand side. Okay. And so what I'm going to do is I'm going to add 4 waters opposite of where my oxygens are. So I'm going to say 4 waters. Now I have to deal with those hydrogens. I have 8 from the water. I have 4 already from the aluminum hydroxide ion. And so I'm only going to add 4 hydrogens opposite that, those 8 waters. I'm sorry, the 8 hydrogens from the 4 waters. Now, so far, this looks like everything we've done in acidic conditions, but now we're doing these in basic conditions. So there's one extra step we need to add, we need to do. We need to add hydroxides equal to the number of hydrogen ions that we added to both sides. So we added 4 hydrogen ions. So I'm going to add 4 hydroxide ions here and also over here. That is literally the only difference or extra step between basic and acidic conditions. All right. So what's going to happen? These are going to come together and form water. All right. So what I'm going to get overall is I'm going to get 4 hydroxide ions plus 4 waters plus my aluminum plus my aluminum hydroxide ion plus my 3 electrons plus my 4 waters. And guess what's going to happen now? These cancel out, and all I'm left with is the hydroxide ion in solution. That is literally the only difference. So once I get to the part that I stopped at with acidic conditions of adding that hydrogen ion, In basic conditions, we are going to add hydroxides to both left and right equal to however many hydrogen ions we added, because we got to neutralize those hydrogen ions. All right. The reason we're adding 4 hydroxides is because we added 4 of these. Those 4 hydrogen ions make the solution acidic. To make it basic, we have to neutralize those hydrogen ions, and we do that with hydroxide ions. But we do it to both sides, leaving us with this in solution. Okay. Now, let's do this for the redox half. Okay. So my bismuths, my BIs, they're good. They're equal. They're 1 to 1. I got 4 oxygens, 1, 2, 3, 4 on the left-hand side. So I'm going to add 4 waters. Now I have 8 hydrogens on the right-hand side. So I'm going to add 8 hydrogens opposite that. Now, because it's in basic conditions, I have to add the hydroxides, 8 of them, to both sides of the reaction. So we're going to say 8 hydroxide ions plus 8 hydrogen ions plus that. Plus that. Oops, forgot my 4. Okay, we're almost done. Now all we got to do is balance out the electrons. Okay, so in my oxidized half, I got 3 electrons, and my reduced half, I have 5. So I'm just going to multiply my oxidized half by 5. I'm going to multiply everything by 5. So we're going to have 20 OHs plus 5 aluminums plus 5 AlOH 4 minus plus 15 electrons. And now I'm going to do the same to my reduced, but I'm going to multiply this side, these by 3. So 24 hydroxides. Actually, let me do this. Let me get rid of the waters first, so we don't get confused. Okay, only 4 of them canceled out. All right, so now we got 4 water, so 4 times 3 is 12. Oops. Okay, so what's going to cancel out? Okay, so all of these are going to cancel. And I'm going to be left with 4 hydroxides here. All of the electrons are going to cancel. All of the rest stays. The water is already as canceled as it's going to get. So my overall balanced reaction will be 12H2O. So annoying where it does that. Plus 5 aluminum plus 3 BiONO3 yields 5AlOH 4 minus plus 3Bi running out of room plus 4OH. And what makes this in basic conditions is now that right there. We neutralize the hydrogens that we added. So we have leftover, leftover hydroxides in solution. And it, that's what's going to give it the basic conditions. All right. Okay, that's all the problems we're covering today. This was recorded if you came in late, or if you had, if you got kicked out and had to come back in, or what have you. There was an issue with Collaborate today. I couldn't get my stuff up and running. So this is recorded. It's going to take a minute for it to download to my computer, and then a minute for me to upload it so I can get it up into Blackboard for you guys. So you will be able to go back and watch the whole thing. As a recap, hold on, let me just do this. Okay, as a recap, my surgery is Tuesday. So if I can't get one of the D'Antonios to sub for me to continue on with chapter 19 lecture, then I'll go ahead and put a lecture video up and with a corresponding assignment. But I've been reaching out to them and they're checking their schedules. So hopefully one of them will be able to cover for me on Tuesday. Any questions about that? Okay. Also, just an FYI, for chapter 19, your focus needs to be what we just went over today. And then the voltaic cells, basically, how it's set up. I am going to put supplemental videos up for you, regardless of whether or not I put a lecture video up or you have a sub. It's an animation of the electrolytic cell. It's very, very well done. I couldn't even come close to drawing the way that it's done. So do take time before lecture on Tuesday to do that or to look at it. No assignment with it, nothing like that, not for a grade. It's just visually, it's a very well done animated thing to show you how the voltaic or galvanic cells work, okay? And so you're going to focus on that and then cell potential. And for chapter 19, that's pretty much all I'm having you focus on. Your Pearson assignment for chapter 19 is up and ready to go. Like I said, it was going to be a little bit longer than the usual because you're not being tested on it before your final exam. And your final exam will be written before the end of this weekend. Okay. I'm going to try to get all your tests graded tonight. Also, I'm about halfway through grading your tests. Okay. Questions? Nothing? Okay, give it a few minutes and this will be uploaded into Blackboard. It just takes a minute to download and then re-upload and all that kind of stuff. There's no good way just to get it from Zoom into Blackboard. But it will be up there for you guys to view. I will put it probably, I think I'll put it in everything you need, in class problems, worked problems. That will be where I put it, okay? All right, you guys have a wonderful, wonderful break, and I will hopefully see you towards the end of next week. We'll see though. All right.